Okay guys, I wanted to do another video here. This one's going to cover the precipitation part of the chapter. And so in a precipitation problem, what you have is a non-equilibrium situation. And as you recall from our discussions of equilibrium, when you're not at equilibrium, you can calculate a quantity that sort of looks like the equilibrium constant, but it's using the non-equilibrium concentrations, and we call it the reaction quotient. So these types of problems involve calculating the value of Q for a given set of non-equilibrium conditions, and you compare that Q to the equilibrium constant, and based upon that comparison, you can predict which way the reaction needs to go. For dissolution reactions, such as this one for lead-2 chloride, if the reaction moves towards the left, that results in the formation of a precipitate. If the reaction moves to the right, then no precipitate will form. So what you do, usually you are given the value of KSP, which is defined for the equilibrium concentrations of the ions, and then you're given a set of initial concentrations. And you use those to calculate the value of Q, you compare it to K, and depending upon how Q is compared to K, you make a prediction about which way the reaction has to go. For the case where the reaction quotient is less than the equilibrium constant, that means that the reaction will proceed towards the product side and no precipitate will form. If you happen to calculate Q and it equals KSP, that means that the reaction, the dissolution reaction is at equilibrium, and so there's no preferred direction for that case. The third case is when Q is larger than KSP, in which case the reaction will proceed towards the reactants, resulting in the formation of a solid precipitate. These conditions can be summarized in this visual mnemonic device here, where if Q is less than K, you write Q to the left of K. In order to get back to equilibrium, the reaction needs to proceed towards the right, that is, towards the products, so no precipitate forms. On the other hand, if Q is larger than K, you write Q on the right-hand side of K, and in order to get back to equilibrium, the reaction needs to proceed to the left, towards the reactants, which involves the formation of a precipitate. So let's look at an example problem here. We're considering the dissolution reaction for magnesium hydroxide. And so we have a sample of seawater that contains magnesium ions at a concentration of 0.0537. And you can pull those magnesium ions out of solution if you add a strong base. And if the concentration of the hydroxide gets high enough, then you'll form the precipitate magnesium hydroxide. And so the question in this problem is a concentration of hydroxide equal to 0.01 large enough to cause precipitation to occur. So here's the dissolution reaction that we need. Here is the expression for the reaction quotient. You plug in the given concentrations to calculate the value of Q, and then you compare this value of Q to the KSP. In this case, we see that the value of Q is quite a bit larger than the value of KSP, so we're in the situation where we would write Q to the right of K, and we see that the reaction needs to go to the left in order to get back to equilibrium. That will result in the formation of the magnesium hydroxide precipitate. This is here's a series of problems. The first two are basically identical to the last problem. However, this third problem is a little bit different. And what I wanted to point out about this one, as you can see in the setup, they mention volumes of different reactants. So in this case, you're adding 20 milliliters of a potassium ion solution to 80 milliliters of a perchlorate solution. And that including the volumes in the problem is a dead giveaway that you need to drop down to the mole level and recompute the concentrations. So because when you add 20 milliliters of a solution to 80 milliliters of a different solution, the total volume is going to be 100 milliliters. And so you're going to need to recalculate the concentrations of the species involved before you calculate the value of Q. So here's the dissolution reaction that we're interested in. It's the precipitation of potassium perchlorate. They give us the KSP. It's a rather large value, and that's because this is a group 1 cation. Nevertheless, we can still work this problem as a dissolution reaction. In order to calculate the potassium and perchlorate concentrations, we need to drop down to the mole level. So we're going to take the volume and the concentration of the potassium ion solution, multiply those together to give us the moles of potassium ions, and then divide by the new volume of the solution to give us the new concentration of potassium. And so here's the number we get for that calculation. And we do the same thing for the perchlorate ion concentration. In this case, it's 80 mils times a 0.5 molar solution divided by that 100 mils for the new solution to give us 0.4. Then we take these concentrations, plug them into the expression for Q to get a Q value of 4 times 10 to the minus 3. We compare that to KSP, and we see that in this case, Q is less than KSP. So we would write Q to the left of K, and in order to get back to equilibrium, the reaction needs to proceed towards the right, which is towards the dissolved ions. So in this case, no precipitate will form. This problem is of interest perhaps to the pre-health professional students in the course. Here we're talking about the collection of blood samples. And what you don't want is you don't want the blood to clot in the collection tubes. And so the reason why the blood clots is due to the presence of calcium ions in the blood. And if you can pull those calcium ions out, then you can prevent the blood from clotting. And so this can be accomplished using oxalate ions. So if you add a sample, a salt containing oxalate in it, what will happen is the oxalate will form a precipitate with the calcium, pulling the calcium out of the blood, and then the solution left behind won't clot, or at least not as easily. And so if you have a sample of blood serum and the concentration of calcium ions is 2.2 times 10 to the minus 3 moles per liter, what concentration of oxalate do you need to establish in order to get the calcium oxalate to precipitate? So here is the dissolution reaction for calcium oxalate. We know it's KSP. And so here's the KSP expression. KSP is known, the calcium ion concentration is known. What is the oxalate concentration at the threshold of precipitation? We solve this equation for the oxalate concentration, and we find it has a value of 8.9 times 10 to the minus 6 moles per liter. This is going to be another example, just like the last one. So I'll leave this as an exercise for you. This is a similar problem, only there's an extra step at the end involving a pH calculation. And so here we have, it's a discussion of manganese ion in, if it's present when you're washing clothes, the manganese ion can stain the clothing. And so you'd really like to precipitate out the manganese so that it doesn't stain the clothes. Here it says if the concentration of manganese is 1.8 times 10 to the minus 6, that's when you're going to run into trouble. So let's assume that we have that much manganese present in the solution. The question is how much hydroxide do we need to add in order to precipitate out this manganese 2 hydroxide species? So here's the dissolution reaction of interest. What we want to do is to force this manganese hydroxide to precipitate out, and we want to know what is the pH at which that will occur. So we write down the KSP expression for this dissolution reaction, and we solve it for the hydroxide ion concentration, very similar to what we did in the previous example that I worked out, and you get a value of 3 times 10 to the 4th moles per liter, And then what you do is you take that concentration and you calculate the pOH here, and then you subtract that from 14 to give you the pH required to force the precipitation to occur. Here's another example. This one involves magnesium hydroxide. I'll leave this as an exercise for you to work on. And then I think we'll stop this video right here.